For our lesson 8.10, nonlinear systems. Start off with saying review. We've already solved systems of equations. We've solved linear systems of equations. Anybody remember that back in chapter 5? We solved them by graphing. What did we look for when we were graphing? We used the slope and the y-intercept form probably to help us graph our lines, but what did we look for when, because the system of equations is two or more equations. So, pardon? No, we did. They do have a domain and range, but that isn't the solution. Brady?
Wasn't like the parent stuff?
Well, the linear family does have a parent function, but that's not the solution. We also solve by substitution. Maybe that'll help. We also solve by adding them together, called an elimination method. And every time we did it, we got an ordered pair answer if there was a solution. No, should we try this again? Do you think you know how we found it by graphing? No? This is what we did. If the lines intersected, because those two equations were working together, that point of intersection was considered the solution of the system, because it's the only x value and the only y value that made the two equations true. It satisfied both of them. So it was an ordered pair solution. When we solved it by substitution, same thing. We got an ordered pair solution. We were really finding the point of intersection on the graph. When we solved it by elimination, same thing. We added them together and got a variable to eliminate. That's the same thing we were doing there. So what should happen today is we should get ordered pair answers. Okay, so let's just fill in here. A system of equations is two or more equations working together. So a system of equations means you have two or more equations and they are working together. And the reason they're working together is because there's more than one variable for you to solve for, and it's a good way to help us be able to solve for two or more unknowns. Notice it doesn't say a linear system of equations, it just says a system of equations. In other words, both equations, none of the equations have to be linear. So our solutions for them are the points of intersection. So wherever the graphs intersect, that's what we're going to consider to be the solutions. Well, that can be no points, 1 point, or I probably would just put the 2 in the first blank here, so we'll put this word in here, or 2 points. In other words, there might not be any place where they're going to intersect. No points of intersection, 1 point of intersection, or 2 points. And you have your book open to lesson 8.10. Why don't you take a look at the middle of that first page on that lesson. Do you see those situations happening there? You see the first graph, what is that? What do you think is the situation going on in the first graph? Are there any points of intersection? No. So would there be any solutions? No. How about the second graph? How many points of intersection do you think there are? There's actually only one. The vertex is actually sitting on that line, and the arm of the parabola looks like it gets really close to it, but it really isn't crossing it. So there would be 1 point of intersection there. When the vertex is sitting on the line, then you're only going to have one solution. And when the parabola is crossing, in the third graph, when the parabola is crossing the line, those 2 points where the arms of the parabola are crossing, those points of intersection are considered the two solutions. So when we have nonlinear systems, that really means, what did I want to put there? I don't even know what I was meaning there. Not all equations, okay. Nonlinear means not all equations are linear. Maybe not, in fact, maybe none of them are. But if you have a nonlinear system, they're saying it's going to not have just, it's not going to be treated as two lines intersecting. It might be one of them a line, the other one a parabola. And that's what our case is gonna be, the ones that we're solving in this lesson today, okay? So let's practice solving them algebraically. Then we'll check them with our graphs, okay? With the graphing calculator. So I say we're gonna solve this system of nonlinear equations by substitution. Why did I choose substitution, do you think? Back in chapter 5, when we were doing linear systems of equations, we said if one of the equations is solved for either x or for y, you can take that expression it is equal to, circle it, substitute that into the other equation. Remember that? Remember us doing that? Okay. So what we have here is we have, what kind of a function do we have right here? Is that linear? No, that one's what? Quadratic. So that one should create, what on the graph? If we were graphing this, what would it create? Jared? A parabola. Would that parabola open up or down? Up. Okay, so let's just say, you know what? We know that on the graph we'd have a parabola opening up for that one if we were solving it by graphing. How about the other one? What's true about this function? Is that one quadratic also then? What's that one? Linear. What would that one do on a graph? Make a line. Would it rise or fall from left to right? It would rise. So we would have a line with this kind of behavior. So we're gonna solve it algebraically, but what we're really looking for algebraically is, are there any points of intersection? Are there any x and y values that can be put together as ordered pairs that show what's happening with this parabola and this line on the graph? Well, since both of these are set equal to y, we can just take our expression from the first one and substitute it into the other equation for y. for y. So let's take our x squared and minus 2x minus 5. And we're going to put it in place of the y in the second equation. That's what we just did. So now we're going to set that equal to 2x minus 8. So we just basically are taking the second equation and renaming it. We're taking what the first equation, because they're working together, what the first equation was equal to, putting it in the second equation for the y. Now, because there's an x squared in there, and an x term, and a c term, this is quadratic, isn't it? How do we, now we have to solve a quadratic equation, which is what we just learned how to do in this, earlier in this chapter. That's what we've been doing. So what do we have to get this equation, Courtney? Equal to 0. We need it in standard form, equal to 0. So what should we do? Subtract 2x and add 8. Subtract 2x and add 8. We're just doing the same thing on both sides. So now we will have x squared, what?
Plus
Plus what?
Subtract 4.
That's actually going to be a subtract 4x, isn't it? So if you need to, let's change this to add the opposite, add the opposite. We really have a negative 2x and a negative 2x, which adds up to a negative 4x. And what do we have for our subtract 5, add 8? That would be plus 3, wouldn't it? And now on the other side we have our 0. Okay. Well, now's when you get to do the method you like best. So you're going to try solving it by factoring, solving it by quadratic formula. I'm going to say, if you want to go ahead and do the quadratic formula, you can. I'm going to tell you right now, this one's factorable. I'm going to factor it. So, A, B, and C. It doesn't matter which way we're going to use. We're going to identify our A, our B, and our C. What is our A? 1. B is negative 4, and C is 3. I really like the fact that factoring for this one because A is 1. That means I only have to use the diamond method and I don't have to use the factoring by grouping because I just have to find numbers that multiply to be positive 3, add up to negative 4. What are they? Negative 3, negative 1. Okay? So that means I have renamed my quadratic function as what? What would its factored name be?
X minus
X minus 3
times X minus
times x minus 1. There's my new name for the quadratic function that we're working with. Okay? But now I still need to solve for x, right? That's what we're doing, we're solving this. So how many solutions is this one going to have? Two. So we have x equals what? What's this one? What makes this factor equal 0? Remember that? Okay, let's do it. Let's do this. X minus 3 equals 0. X minus 1 equals 0. Add 3 to both sides of this one. What are we going to get? X equals 3. Okay, there's one of our solutions. Right now we're just finding the solutions of the quadratic function, but we're not doing that. We're finding for the system, working with that line, so we're going to carry on after this. What's this equal? 1. Okay. So what we just found, you guys, is we just found the x values of the points where the parabola is going to cross the line. We just found the x values of the points where the parabola is going to cross the line. So what do we need to do next? We have to now find the y values, don't we? So we have to find y for x equals 3 and for x equals 1. We have to do it for both of them. There are 2 points of intersection apparently. So we'll take our where are we going to do that at, do you think? Do you think it matters? The equations that we have at the top. Do we have to do it in both of them, do you think? What did we do when we were solving systems of linear equations? Did we get to pick which equation we wanted to use? Why? Yeah, they're working together, aren't they? This is a system. They're working together. One's, likes the other. They're okay with each other. So why use the quadratic when we can use the linear, right? Why not use the linear? Y equals 2x, what was it again? 2x what? Minus 8. Okay. So we're going to do y equals 2x minus 8, and we're going to do it for both of our x values. So 2 times 3, that's our first one. Take away 8. Well, that's 6 take away 8. So y equals what? -2. Now, before we move on, we're going to write that as our ordered pair solution. Remember, we're looking for points of intersection. So what ordered pair is that? 3, -2. There's one of our solutions right there. And now we'll go and do the other x value we got, which is 1. And we get y equals 2 take away 8. So what's this one? Y equals -6. So what's our other point of intersection? 1, -6. Okay, now we're going to verify that was correct. Okay, so what do you do? Y equals screen. In y sub 1, put one of the equations, and in y sub 2, put the other one. So the quadratic function can go in one of them. It doesn't matter which one goes in which. One's not more important than the other. So we have to put in our quadratic in one of them. X squared minus 2x minus 5. And in the other one, we're going to put our 2x minus 8. Do a zoom 6, that'll give you a nice standard window. Do a zoom 6. And eyeballing it, what do you think? Do you think, first of all, are the parabola on the line, do they have the behavior we thought they would have? Yeah, okay. Is the line crossing the parabola or vice versa? Yeah, in 2 spots? Okay. Does it appear just by eyeballing it that one of the points of intersection is our ordered pair that we got at the bottom here, we got 3, -2. Isn't that what we got? Yep, 3, -2. Eyeballing it, does it look like the line of the parabola crossing an ordered pair 3, -2? Yeah? Okay, and then how about ordered pair 1, -6? So we found it algebraically, but we're checking it with the graph. Do you think we can find it with the graph also? Yeah, we could, but remember that solving by graphing, we're really saying we think this is what it is, but it could just as easily have been like -3, comma, or +3, I mean -2.1, we don't know. But algebraically, it will get you the exact answer, and then we can look at the graph and say, oh yeah, it looks like that is what it is. Okay? So, anyone have questions? Okay, we're gonna do another one together. Go to the back side. Okay, we have y equals x minus 5, we have y equals x squared plus 2x minus 3. Oh, what do you guys think? Is the first one, what kind of a function do we have here? Linear. Is it gonna rise from left to right or fall? Rise. Okay, so this is what we should expect on the graph. How about the second equation in our system? Is it linear, quadratic? Quadratic, so it's a parabola. Would that parabola open up or down? Up, okay. Okay, so we're going to go about solving it algebraically. We're going to use, again, they're both set equal to y, so use substitution. So we'll take what's in the first one, put it in place of the y in the second one. Again, it does not matter which side of the equation the zero's on. I would always just move, the side so that you end up with a positive a value, because then if you can solve it by factoring, you have a positive a, and you don't have to do the factoring by grouping. If a is a +1, so we're going to. This is really x plus a -5, so we would subtract 5, and we would subtract x and add 5. Subtract x, add 5. 0, x squared plus what? X plus 2. Okay. This one, let's get our a, b, and c identified, and then we can go from there. So we have a equals 1, we got b equals 1, we got c equals 2. Okay, so that means if we do our diamond, I'm just going to go over here and set it up, we have 2, 1. How are you feeling about that? You think we can do that? Does that mean we stop and say, can't do it? What do you think? No, because what do we have? Do we always rely on if this doesn't work? Quadratic formula. We don't get to stop. We have to now use the quadratic formula. So now we'll say, okay, that's what I've been doing the last couple of days. X equals the opposite of b, there's my b, plus or minus the square root of 1, 1 squared, and then plus our -4, times our a, times our c, all of that over 2 times 1. X equals, the opposite of 1 is -1. We're going to end up with 1 plus -8 all over 2. Well, x equals a -1 plus or minus the square root of what? -7 all over 2. 7 over b squared is the opposite of 7 over b squared. What are we going to do? We're going to do what we did yesterday. Yeah? Really? No solution, why not? You can't take the square root of a negative number. Just go ahead and try it. Top it. He says, didn't work. Whenever we end up with a negative number under a radical sign, we have to stop and say, can't do this. So let's just make that note right here. Can't take the square root of -7. Not going to happen. So that tells us if we can't get any x values for some points, can we find y values? So what's that tell us? There's no solutions, no points of intersection. And we're going to graph it and verify that there's no solutions. See if we screwed up or if we're right. So now go and clear out your y equals. Go ahead and clear out the 2 that we had in there and put in our new 2. What should we expect to happen? That the parabola and the line will what? Will they intersect? They won't. When there's no solution, they shouldn't intersect, should they? This one you should just be able to go right to a graph. You shouldn't have to do your Zoom 60. What's the case? They don't intersect. So apparently we know what we're doing. Now, again, listen carefully to me. It is not because we could not factor it. It is not because we could not factor it. We always have to try, if you can't factor it, then you have to try the quadratic formula and see, because factoring, just not being able to factor it, really, here's what not being able to factor it means. You're gonna have to get approximate x values like happened yesterday. That's what not factoring can mean. It doesn't mean there are no solutions. So you have to go to the quadratic formula and try it. This may happen, this may not happen. Okay? So you have to finish it out. Anybody got concerns? Okay. Then you have 4 problems to do. And here's what I want you, what you're going to do though is, because you're not going to use you don't have a graphing calculator, I want you to solve them. But then I also, if it has, I'll check to see if there are any no solution ones, by the way. If it has a solution, ordered pair solution, you're going to substitute those ordered pairs back in and check them out. Okay, algebraically. We know how to do that. Like, if we, on this front side, when we had, we got positive 3, negative 2, we would put negative 2 in this one for y, we'd put positive 3 in for x, and we'd see if it checked out. Then we would put it in this one and see if it checked out. If it checked out in both of them, we'd say, oh, cool, that's a solution. Then we'd check out our other one, our positive 1, negative 6, we put that in both of them and we checked out. So again, that's why you only have 4 problems to do, is because they take a little bit and then I just want you to check them. Okay, so let's get